No. Yeah. Dude, I hate using like smartphone. uh, uh,
Do you want some chocolate?
oh yeah, Kit Wilson. Kita. Wilson.
We need electricity.
There was one more guy. We should always go bring us chocolate.
How would you this problem?
Wi-Fi was up, huh? Yeah, cool. You can swear. My mind is just in the previous conversation. Here's pretty quick. Let me click my mind. So what is the question again? Can you read the question? Quantum black hole, huh? Okay, we have a guy, and it walks.
It's walk 30 degrees east of north.
East of north is east of north. So this way.
And the force of the wind is 150 Newton.
Do we have the angle?
30 degrees.
Huh.
Then it's 30 degrees up.
Like east
Yeah,
of
that's
north.
what the
Right? East
No.
of north. East of north?
No, it's
It's-
east of north. So it's I think I'm not.
I hate this. 30, right?
Yep. And then if you first walk 110 meter towards north,
So wait. So this guy walks east of north, right? How much?
30 degrees,
Okay, no distance. Okay.
then the second part is that like if he walks 110 meter towards north and then towards east 250 meter.
Oh, so he goes like this and this.
Yes.
Goes like that
Yep.
and like that, right?
Yep.
So what is this distance?
110
110. And this?
250.
250.
Yep. So what is the total work done?
Okay, what is the force of the wind?
150 Newton.
Which way?
The direction, the theta way, 30 degrees towards north of east.
Oh, so it's like, oh, so okay, so this is the force
Mm-hmm.
of the wind being how much? How much is the force?
150 Newton.
150?
Mm-hmm.
Headache right now. Okay, so when you have work done, right? So it it has to be in the same direction as the force, right? So this guy, so if the okay, wait. This guy walks into the north, huh?
A question.
Huh.
So if the work done is in the same direction as the force, then what's the east of the angle?
the thing is that this guy first walks to north, then the east.
Yeah.
But our wind is in the northeast way.
Yeah.
So the thing is, wind has both north and east components, right?
Mhm.
So what I'm thinking is this wind has its own components, so it's maybe it's doing both work in the y direction and the x direction. So like so
Why not we can do like using the distance formula and find, we have the x direction distance and the y direction distance.
oh yeah,
We
so
can
yeah,
find, like,
so why don't we do Pythagoras theorem and find the so work done is
But I got wrong answer with that.
you got wrong answer. So it's like why don't we do so it's like Pythagoras triangle. Take this, and square this, and then
Yeah.
square the whole thing. So the displacement is this one,
Yeah.
Yeah.
and times force.
Yeah. I got the wrong answer.
You got the wrong answer?
Yeah.
That's why I think it's
Huh?
it might be some component. I don't know because the angle is there for a reason, so it's probably maybe wind force sine theta times displacement.
But my question is why this method is wrong? What I did.
What?
Why this method is wrong? What
Why
I
that
did.
your method is wrong? Oh, okay, wait. So the thing is, this guy. So you have force 150, right? The thing is, force is 150 is in northeast, but it has components. So the 150 force has a lower component on the y and a higher component maybe x. But this guy walks in more in the x than in y, right? So what I'm thinking, why don't we just break down the force in components, then multiply with the distance, then add them up.
You know what? We'll
You
multiply
feel me?
by-
It's like so this is force, right? So force W has a y component, right?
Yeah.
Which is 150 cosine
Sine.
30.
Sine.
No, y, it's, the angle is here, so. Which part you didn't understand? If angle was here, you take the sine.
Oh, yeah, yeah.
So y is here, so right? Cosine is adjacent one, always, right? So if wind in x is 150 sine 30, right? So if this guy walks, first he walks north, so the work done from the wind, 110 times the FWY, right? Then he walks to east, then the magnitude of force acting is this one.
I have one more question. In this diagram, what is the perpendicular
What is perpendicular?
and what is base?
To what? Perpendicular to what?
I thought perpendicular is opposite to the angle, right?
What do you mean perpendicular?
The perpendicular hypotenuse base.
I don't understand the question. Like,
In this triangle,
okay,
which one
this is
is
the perpendicular.
This one or this one?
This one. When you have a horizontal and vertical and horizontal, this one is perpendicular.
Okay,
Right?
if we have to take the sine
What do you mean?
perpendicular over hypotenuse, what is perpendicular in this case?
So this angle is perpendicular, right?
What side?
What do you mean what side? I mean, I don't get your question. What do you mean what side? I mean, what do you mean what side? So
Trying to say if the
so-
perpendicular is 250.
so look, we have a triangle like this, right?
Yeah.
This side is perpendicular.
This is the angle.
So the
between
angle
the
is
two
here.
sides. Okay, take the tan theta for that.
Tan theta? Why?
Just I'm asking.
Tan theta is this one. This divided by this. So this is opposite of this angle. This is adjacent, and this is hypotenuse.
Okay, that's what I was asking.
Hypotenuse is always the length across the
Okay, yeah.
across the 90 degrees.
Okay,
I didn't get your question in the first. Make sense?
yeah.
So this makes sense.
Mhm.
So what I was thinking, so if this guy went 110 north, then the magnitude of force acting on him is this amount. So this distance times this force is work done in y. I mean, or the first path. Fwy times 110. But then he walks in the second path to the east, which is he walked 250, and you Fw in x. That's what I'm thinking.
Yeah, on this question, right? Um,
What's up?
alright. So this question says, suppose that the force required to push the saw back and forth give a piece of wood.
Wait, first. Yeah, does it make sense?
Yeah, but I'm still thinking why that method was wrong.
You're still thinking what?
Why the other method was wrong, using this formula, distance formula.
Because you're using displacement from the origin, right?
Mhm.
It's like, so look at this one. It's like I want to go from here to MSV or 20cc.
Mhm.
From here to MSV, we have fixed displacement, right? It's fixed.
Mhm.
It's 100 meters. But the path you take, you can take whatever path you want. You can enlarge your distance. You can take the right, left, and stuff, you know. And instead of going 100, you end up going 200, 300.
But I
So
thought the work done is not dependent on the path. It's just taking the shortest distance.
it's path dependent, right? Yeah.
Is it?
Yeah. Unless it's conservative.
Okay. Okay.
I mean, try this and like, if the answer is wrong, then think something else.
Okay. So you mean the force of the wind is not conservative? That's why we are not doing
Mm-hmm.
it.
Mm-hmm.
Oh.
Mm-hmm. Wi-Fi, what's your question?
So so
From quantum holes to physics, but I'm just like still lost. But anyways, what's your question, bro?
alright. So this question says, suppose the force required to push the saw
How do you
back and
suppose?
forth. So, alright. Can try making this
Okay, suppose that the force required to push a
one. I think the answer should be 0.
back and forth through a piece of wood is 25 Newton. If you push this saw back and forth 28 times, moving it forward 11 centimeters and back 11 centimeters each time, how much work you do?
0.
Right, it should be 0. Oh, wait. You push it 28 times.
Yeah, still 0 because it's moving back and forth. It's not displacement.
But it's not 0, right?
Yeah, it's not 0. I
Okay,
don't know why it's not 0.
so the thing is, okay, every time you push, you add work. You do work, right? So it's like pushing. But you're not like you're pushing 11 centimeters. So you push 11 centimeters right, 11 centimeters back, right, back, right, back, right. You don't think because like every time you push, it's like this problem, you know. You push, you make work. You push back, but basically you're converting your axis from the opposite way, like you're pushing it down.
Mm.
I guess you say,
So was the answer was like your force times 11 distance and 28 times.
okay, so this is basically your force and resistance question, not force and resistance one question.
No, it's like so you're acting force, but it's like again it comes to this conservativeness, you know. Your force is a conservative.
Conserve. Increase if you want that item.
Huh? What's wrong? Pushing forward and back. If you're doing no work, how will you?
Even
If you're doing no work, how can you know? You know.
even in that case, right?
Even in that case, you're doing work.
work done is zero. But like I mean,
No, unless there is no zero, bro. If it was zero,
there's
how
effort,
are we
but
gonna
there-
feel? Huh?
but there's no displacement because it goes up and down.
But you're thinking the wrong way. But in that case, if you have friction and stuff, so like
Yeah.
it's different. But anyways, but you got it right.
Yeah, kind of. I don't want to know why
It's like first there is no field, there is no you can say it's conserved and stuff. So not in this problem.
Yeah, fine.
What
It's
else?
28 times 11.
I think it's 28 times you've applied force and 11 centimeters.
Oh no, it's going to be that times two because we're going back and forth. 11 times 4, 11 times backwards.
The wave function. But you look confused.
Yeah.
Let's be honest. Let's be honest. So I can take another kick out, right?
Why we are
Why what?
why we are just multiplying by 11?
Why we're just multiplying by 11? Why we are not just multiplying by 11?
You said 28 times f dot 11, right?
I mean, I didn't question.
You can take it as well.
Thank you.
It's going back and forth. So 11 times back, 20 times back, 20 times back.
Yeah. It's like you think it's like in mathematical analogy. You can think like the total to be the sum of the works you put, right? So every time you pushed one, you did one work, and you did the second work, you did the third work, you did the fifth work, and you add them up. But in this case, you have all 11 centimeters, so it's like 28 times you did the work, you did the same work.
Okay.
These are good. These are good. Like, let's talk about anything that you guys didn't understand in the class or from questions. Maybe I can explain something.
Last class, so I wasn't in last class.
He wasn't there? Neither.
What was the topic?
Huh?
What was the topic? Others. Yeah, this one too. Coming.
This is the second one, right?
Yeah. I mean, I know the work done on the box. The force is going to be the force of friction, right?
On the box?
Like if I'm putting a box on the work done of me on the box, right? Yeah, the work done I do on the box. The force of
So it's like
the
this,
force of
right?
friction.
You have a box, right? And there's a friction, right?
Yeah.
And this guy is a mass, whatever, you know, mg, fn, right? But you're not moving in y direction. You're moving x. You're trying to move. So to move in x, so you're basically pulling something, right? And if there's a friction, this is not F, this is oh my god. At least we can press. So this is FA, right? You apply some force. Because you're applying force and you're trying to move something, you have force of friction, right? So work done on this case is your F net times the delta x you moved, right? So, so after a certain point, you move the box here, still pushing it maybe, still there's a force of friction applying, but at this distance, at this time interval you applied, you move delta x, right?
Yeah.
So that's the delta x you care about, and for the F net you care about F net, how much actually, like it's like an efficiency thing, you know, like what is your efficient force, right?
Okay.
It's like in basketball you took 55 shots but like 10 scored. But like, you took 55 shots. There's like 55 forces. But what matters is the score.
Yeah.
And the score here is F applied the score here is F applied minus the force of friction times the change in distance you walk, right?
Yeah.
Make sense?
Good. Well, how do you know acceleration?
How do you know acceleration?
Yeah.
I mean, you calculate acceleration if you want to. But this is not the acceleration problem.
Yeah, but you said
You said what?
you get FA minus F. Sorry, is FA F times A?
No, FA
Oh,
is
it's
force
applied
of
force.
applied. Force of applied. And you can say, you know, like FA minus FF is, you know, MA from the constant, you know, it's a constant acceleration thingy, you know.
But how do you find acceleration?
Have you find acceleration from this? If you want to.
Yeah.
Huh?
Yeah. Because you don't have applied force, you have frictional force because you know the normal force and you know the constant of friction. But you don't have applied force.
So how this thing is moving?
Moving this way.
Okay. Okay, so wait. Let's make the question clear, okay? So basically you're telling me we have a box, right?
Well, it moves two distances. It
Huh?
moves. Okay, this is the whole question. A child drags a 15 kg box.
Wait, what?
A child drags a 15 kg
Okay, a
box
child drags it, okay.
at a constant speed across the lawn for 17 meters and along a sidewalk for 32 meters.
Okay.
Then we have the coefficients of friction for the first part and the second part of the journey.
What do you mean first part and second part?
The coefficient of friction when it drags across the lawn is 0.25. But
Also,
yeah,
it has different
yeah,
different surfaces.
yeah.
Okay, makes sense. Okay. So, so what you're saying is there's a kid. Is he pulling at an angle or straight? Good. So, what is the mass of the box?
15,
15. What is mu? 1,
0.25,
0.05,
25.
25. Right? And so the kid is pulling, okay, constant velocity, right? What is the number? Doesn't give a number, okay. So what else he gives?
Just give the mass, the distances, and
What is the distance?
17 for the first part.
So okay,
Change in
so this guy pulls it, comes here, right? This is 17. So, and there's another section with a different mu,
0.55.
0.55 with the same mass is pulling, right? So you have the force of friction 1 here from the something, and you have force of friction 2 here, right? Clear?
Yeah.
Okay, so what else?
That's all.
What was you asking for?
How much work does the child do on the box?
How much work child is doing on the work,
Yeah.
right? Okay, so you know, so this is F, and this is F, right? The F should vary because you have different surfaces. Because you have different surfaces, you may be pulling harder or like lighter. So I mean, I didn't. So it starts from here, right? And it's pulled by 17 meters. Is it meters? So after this, how much it pulls?
32.
Huh?
32.
32? So this is 32. So it's asking for the total work? Okay. He. He didn't give you constant velocity? No velocity number?
I think that's just a way to say that there's no acceleration.
Yeah, there's no acceleration. Oh, yeah, okay. So it's constant, right? Which means acceleration is 0, right?
Yeah.
So because you know acceleration is 0, and these things are moving to the right? So first part, you write the equation of motion, right? Being F1 minus FF1
Equals
equals MA, which in this case this is 0. And you know FF1 being mu1 times Fn, right? And Fn being equal to mg. Cool beans? So
Wait. Fn. Oh yeah. Sorry.
the normal force,
Yeah.
F force of normal. So F1 is basically
That's 36.7.
mu1 and mg.
Yeah. That's 36.7.
I'm not going to put any numbers. Oh, you got it, right?
Yeah.
Second part, same thing. Second part, again, you have F2 minus FF2 being equal to MA, but still 0, right? I mean, unless it says something else. So F2 is FF2, which is mu 2 mg.
That's 80.9.
Right? So work done, again, sorry, again, total work done is sum of the work done through the path, which is, so in the first part, the work done is mu 1 mg times delta x1. The second part, mu 2 mg delta x2.
I don't think you can answer. I did that at first, but I don't think you can answer.
What do you mean?
It says it's wrong.
This is wrong?
Yeah, that's what I did at first, but it says it's wrong.
Are you sure you do the same things?
Exactly. When you get F1, you get F2, then you add both of them up. When you get two force of one force of eight.
The coefficient of the first part of the trip and the second, 0.55. Okay. If the child always pulls horizontally, how much work does the child do on the box? I think you calculated wrong, bro.
I mean,
Do the thing.
Alright, let me do it again. That's MT.
Constant speed.
15 kg, right?
So it's 15 times 9.81 times 0.25 times 17. Plus 0.55 times 9.81 times 32. I think I calculated wrong. This should be right. This is right. I mean, as long as I'm concerned.
Okay. Oh yeah, I did calculate wrong. This plus this is not 70.
Stop paying attention to basketball.
Shut up.
But you look unsatisfied. Like, let me be honest with you.
What?
You look unsatisfied.
No, I didn't calculate. I just understand the.
You got it, right? Well, it feels like you have a question.
I have the other question.
Okay, one more question and it should be done. But
Okay. So, question
Just-
number 9B.
9B? What is 9A?
Okay. So it's
So what is
a
9?
mass of 130 gram attached to a spring with the spring constant 22 Newton per meter. And it says that it passes through its equilibrium position and its speed is 3.8 meter per second.
Hmm.
For the first position, we had to find the work done at equilibrium position, and for the second, we have to find the magnitude of initial displacement.
No, it's initial displacement. Okay, you did the first one. Something like that, right? So
Spring constant is given.
I mean, first, where you push it, left or right?
It doesn't say.
So it pushes
It
it
says
somewhere.
it displaced from its equilibrium position and released from rest.
Okay, I mean, if you push it that way.
Yeah.
So you push it that way, left, right?
How do we know?
Doesn't matter. Doesn't matter. So because the springs, they're weird because they don't have any specific direction. If you push it to the left, the force is to the right. If you push it to the right, the force is to the left. So it doesn't matter. What matters is spring always wants to like act on the opposite way as being acted or something, like some philosophical explanation. So you push it to the left, and here is the X naught, right? So this guy will push it to the right, Fk. We have the mass, right? Yeah, we do. Okay. So
Now when it's released, its speed is 3.8 meter per second when it passes the x0.
So when this guy passes here, it's 3.2.
3.8 meter
3.8 is a constant speed.
It just says its speed.
Speed. It can't be constant because like there is no other force acting on it, so there should be an acceleration. Okay. So this is x1, right? Which is a 3. What?
It's not given.
So x1 is not given.
No.
So I'm trying to understand the question. So v1, no. So v is measured at x0. So okay, this guy will come, pass this point, and go this way. It's oscillating, right? So at this point, v0 is 3.8.
And we also have to find the initial displacement.
Yeah, we want to find x1,
Yep.
right?
Yep.
The thing is springs. So if this guy was pushed to the left, right? Let's say. So this guy came here. Once you release it, it will come this way, stop, come back, stop, come back, right? Because I'm guessing there's no other forces. So if this guy passed to this point, it will stretch to the same point, being x1, same distance, right? Makes sense, right? So the force we have is k times x, right? Delta x. Right? Which is this part. And you found the work done, right? Which you take this and multiply with delta x. You said k times but you don't know the delta x, right?
No.
So what did you do?
I think
Find
something
work done.
else.
Huh?
I didn't use this one because we didn't have the delta x.
Yeah, so what did you do?
I drive a formula which I forgot.
So okay, let's think. Work done is force times delta x, right? Work done has same units of
mv square.
has
Kinetic
same
energy.
huh?
The kinetic energy.
Kinetic
formula,
energy?
I guess.
So work done has the same units of energy, right? So when you
Yeah.
put this here, it's k delta x squared, right? So we know what's the initial point.
Yeah, I used the half mv square to find the work done. Because we have the velocity and mass.
Okay, so okay.
And
So
acceleration.
we know that energy is conserved, right? So if you said 1/2 mv square is the work done, why would it be equal to 1/2 k delta x squared? Because this 1/2 k delta x squared is the energy of the spring. So it means, look, it means while you're passing through the original point, right? Your spring force, your spring energy is 0. So at this point, you all have kinetic energy. So when you stretch out, your kinetic energy is 0 because you stop, right? It's like a pendulum. In pendulum, you have a ball here, right? So it swings back and forth, right? At this point, you release it, right? So your velocity is 0. It comes by, and once it's at this point on the other side, stops again, right? and then it swirls again.
Mm.
So it's like that. It comes here, stops because the force of the spring is big. It pulls it back.
Mm.
It's a conservation of energy. So you cancel 1/2. Delta x square should be nv square over k. What do you think?
Okay.
Make sense? Conservation of energy? Not conversation, conservation.
And then it doesn't.
So I'm getting energy cut, right?
Doesn't work that.
You have, okay, you have a question.
Um, so that's how we will find the position.
Sorry?
That's how we will find the position.
Yeah.
I think the final position is 0.
No, it's not 0. It's not 0. It's asking for this position. X1.
Just what was the magnitude of initial displacement?
Magnitude of initial displacement? Initial displacement.
Okay.
Because you can't say it's 0 because this thing will go forever. Oscillating.
It's on, it's 5 o'clock.
Yeah, but just give you some minutes. Some Wi-Fi? Oh.
It's like there's something, yeah.
Huh?
Let's say there's something, and okay, let's say this.
Let's say there is something.
Yeah. if I do work on this pen,
Okay.
this pen is taking more from me.
No, it's not force. It's like, so just look at the definition of work, right? Definition of work is force times distance, right? If you're not moving any distance, how can you make work? Makes sense, right? So like, it's like moving a chair, it's like moving a table. It's like, even though forget everything, it's like moving yourself. If I'm standing here, I'm not spending any energy except the gravitational energy, so I can stand up. If I want to move, I'm spending more energy, right? It's like playing basketball. It's like running, right?
Yeah.
So
Okay. How about
Spend
like
energy.
when you're doing work against gravity? What about
what do you say?
doing work against gravity?
Against gravity, like your chair is doing right now.
It's not normal force.
Yeah, but
Our
Right.
chair is working.
Huh?
There is no displacement in the case of chair.
can you say this?
Oh yeah, please.
There is no displacement, but because there is no displacement, that's because gravity force is not strong enough to pull you down.
So the
No,
work
I
is
mean,
0,
like-
right?
I mean the work done on gravity.
Technically, your chair is doing work against gravity just by holding you like that. But if the gravity was stronger than the chair, it will break down, so gravity will make work like network on you. Like thinking philosophically, like technically your chair is doing work. It's trying to do work at least.
Okay, so
So that means the work done by the chair is opposite and equal to the work done by the gravity. That's why the network is 0.
No, it's the forces are different. That's
in
why.
this case, right? If I show this pen off, all it was doing was doing work against gravity, right?
Yeah, you're doing work against gravity.
Yeah, how do you find out?
How you find out the? I mean,
What acceleration is it for?
acceleration is same. Acceleration is the gravity. With gravity, right? So,
So
but
the
if,
acceleration
So
of this is
F
like-
is equal to mg, acceleration is equal to gravitational force, and
So
the
mgx.
distance is h.
So
it's
mgh.
mgh.
there's a name for this gravitational potential.
Yeah, that's potential energy. Yeah. Oh, yeah. I use kinetic energy. Alright.
It's like, like you throw something, right? And this is your delta H, right, Wi-Fi?
Yeah.
So here's your gravitational potential. And all you're doing is taking it from one grid to other ones. That's how you're doing work. And each one is like, I don't know, like mg different in scale, so mgh, right? All you're doing is taking one from one level to another level in distance.
I think I'm that. You come to number 3.
Huh?
You come to number 3.
What?
You come to number 3.
Yeah, but we have to go to the place in my class.
Oh.
Let me see. A record of the stair climbing.
Hey, can I have another kick?
Sure.
Take the whole bit, bro.
I can take a whole bag.
The record of stair climbing was achieved by a man who raced